Please welcome the Senior Vice President of AWS Utility Computing, Peter DeSantis.
Good evening, and welcome to the first night of reInvent 2022. I think it's been 3 years since we did this live in our customary time slot. And earlier this year, we debated whether to bring back the Monday night tradition. And when the NFL announced the 2022 football schedule and the Seattle Seahawks didn't have a Monday night game, it seemed like the sign we were looking for. So we're super happy to be back here on Monday night with a great band, beer, and of course, some fun things to talk about. Now, for those of you who have not joined us here on Monday night before, what we like to do is take a peek underneath the hood. And we like to do that because, well, it's fun to look under the hood. But it's also important for you to have a look underneath the hood so that you can understand the how that we build AWS. Because the how is important. The how is the way we deliver some of the most important attributes of the cloud. Security, elasticity, performance, cost, availability, sustainability. These are not simply features that you can launch and check off the box. These are things that are fundamental to how you build services. And they accrue from long-term investments. And you can't tell these things exist from a simple point-in-time comparison or looking at the manual. So we spend time giving you the visibility into how we build AWS services so that you can rest assured that we are committed to remaining meaningfully differentiated on these key attributes. And tonight, I want to focus on one of them in particular, performance. Nothing shouts performance like a Formula One car. But performance isn't just about what you can see. And in fact, later tonight, we'll hear a bit about the decisions that Ferrari is making to win races in subtle ways that you cannot see. Great performance is the result of innovating from the ground up and then continually investing over time and being committed to performance. And like a good novel, interesting performance engineering has tension. With a cloud computing system, we need to balance things like security and cost, as well as we seek peak performance. There are typically easy ways to get good performance if you're willing to compromise on security or to blow up your cost structure. But at AWS, we never compromise on security, and we're laser focused on cost. So how do we improve performance while also improving security and lowering cost? Well, there's no better example of this than Nitro. Nitro is the reason that AWS got started building custom chips, and it remains one of the most important reasons why EC2 provides differentiated performance and security. We use specially designed AWS chips that we call Nitro chips to build something that we call a Nitro controller. Every new EC2 instance introduced since 2014 has a Nitro controller. The Nitro controller runs all AWS code that we use to manage and secure EC2 instances, and to virtualize our network and storage. And there's a number of benefits to Nitro. First, Nitro helps us better secure our EC2 instances and provides security capabilities, like Nitro enclaves and line rate encryption and storage encryption. Second, Nitro makes it easy for us to turn any server into an EC2 instance. And this is the main reason why we have so many instance types. Intel, AMD, Graviton, even Mac hardware. And of course, Nitro helps us improve performance. By running all our AWS code on the Nitro controller, we can allocate the resources of the EC2 server for customer workloads. And this provides the highest performance because it completely eliminates the virtualization overhead. And Nitro helps us with performance in other ways. By doing all the network and storage virtualization on the Nitro controller, we reduce performance variability because we can use dedicated specialized hardware for that processing. And these improvements to performance bring sustainability benefits as well, because they allow us to increase utilization and reduce energy usage across the fleet. Now, Nitro is not a new story. Quite the contrary. We've been working on Nitro for the better part of a decade. And in that time, we've released 4 generations of Nitro chips. And each subsequent generation of Nitro chip has provided better performance on a number of important dimensions: lower latency, higher throughput, the ability to handle more packets per second. And we added features too, like line rate encryption. Performance can be hard to improve when you refuse to budge on things like security and cost. However, that's exactly what we've been doing with Nitro. But of course, we're not done. And that's why tonight, I'm excited to introduce the latest generation of Nitro chip, the Nitro V5 chip. Now, this new Nitro chip continues the tradition of delivering significantly improved performance. Nitro V5 is an impressive chip. It has about twice the transistors as the previous generation Nitro chip, which gives it about twice the computational power. It also has 50% more memory bandwidth and a PCIe adapter that provides about twice the bandwidth. And all of this means that it's able to support 60% higher packet per second rate with a 30% reduction in packet latency. And my favorite part about all this is we did it while reducing overall power. And what fun would it be for me to announce a new Nitro chip if we didn't have a new EC2 instance for you to try it out on? So, I'm excited to announce the C7gn network-optimized EC2 instance. This is the first instance that'll be based on the Nitro V5 card. The C7gn is a Graviton 3-based instance designed to deliver improved networking performance for the most network-intensive workloads. The C7gn will provide 200 gigabits per second of throughput and up to 50% higher packet processing performance over previous generation C6gn, which was our last network-optimized instance. Now, while lots of workloads will benefit from the improved performance provided by Nitro V5, high-performance computing applications will benefit the most. For example, weather forecasting, life sciences, industrial engineering. But these applications don't just require faster networking. They also need the fastest processors. And so we asked ourselves, could we pair our new Nitro V5 chip with a processor that was specifically designed to cater to high-performance computing workloads? And of course, we started by looking at Graviton. When we built Graviton 3, we optimized the chip for the performance of the vast majority of workloads that were running in the AWS cloud. And this meant making careful data-driven decisions about performance. There's that tension again. Great performance, low cost. And that's why Graviton 3-based instances use up to 60% less energy for the same performance as comparable instances, while providing 25% better performance than Graviton 2. But HPC workloads are not usual workloads. They do different things. And many of them do a lot more floating point and vector math than normal applications. Graviton 3 is already pretty good at these sorts of operations, but we asked ourselves if we could do better. And that's why we built the Graviton 3E processor. The Graviton 3E processor is a variant of the Graviton 3 processor that's specifically optimized to do more floating point and vector math, the types of math that's very common in high-performance computing. Compared to the Graviton 3-based instance, it does 35% higher performance on HPL, which is a computational benchmark for linear algebra, 12% better in GROMACS, which is a molecular modeling library, and 30% better on common financial options models. Okay, so we have a new Nitro chip and a purpose-built HPC processor. So of course, we're gonna have to put these two chips together. So tonight, we're pre-announcing the Amazon EC2 HPC7g instance. The HPC7g provides the networking capabilities of the Nitro V5 chip with the new Graviton 3E processor. With the HPC7g, we offer even better price performance combined with leading energy efficiency for a host of real-world HPC applications. Customers like Rescale, Arup, and the Water Institute are all excited about HPC7g and how it will help them provide faster and more effective HPC applications in the cloud, whether it's for fluid dynamics, weather predictions, or other HPC applications. Now, new hardware is always exciting. It's one of my favorite things. But performance improvements come from innovations that involve more than simply hardware. There's a dance between hardware and software to deliver the peak performance that we look for. And Nitro has some really good dance partners. For HPC, that dance partner is the Elastic Fabric Adapter, or EFA. EFA is an AWS custom networking interface that's designed to work with the Nitro controller to provide the lowest latency and highest throughput networking in the AWS environment. And to enable this sort of networking, EFA allows us to bypass the kernel networking stack and instead interact directly with the Nitro controller. This avoids the latency and performance variability that comes from context switching and copying of memory with traditional networking protocols. Of course, programming with EFA is a little different than using traditional networking protocols like TCP. So only the most performance-sensitive applications spend the time to rewrite their applications to use EFA. But we've made this easy by integrating EFA with the most common high-performance computing and machine learning frameworks like Intel MPI, OpenNPI, and NVIDIA Nickel. More and more customers are using EFA to reinvent their high-performance computing workloads, like Rivian, who uses computer-aided engineering tools to extend vehicle range and maintain high safety standards. Changes that used to take days now occur in minutes. Or Flying Whales, who builds huge airships to move heavy cargo more efficiently. They run computational fluid dynamics models on AWS 15 times faster and at lower cost. But EFA is more than an optimized host networking library. EFA is also designed to enable applications to get the lowest latency and the highest throughput from the AWS network. And to do that, it uses something called SRD. SRD stands for Scalable Reliable Datagram. It's a networking protocol that we've developed at AWS that's purpose-built for consistent low-latency networking in our computing environment. Let me briefly recap how SRD works. To understand how SRD works, we need to understand a little bit about data center networking. Data center networks are essentially trees of routers, where the servers are connected at leaves at the bottom of the tree. In a traditional enterprise data center network, routers were expensive and had limited capacity. So these networks relied on oversubscription. This was a sensible way to build a network a decade ago, especially given the high price of data center networking gear. But this sort of oversubscription is not what you want in the cloud. So this is not how we build the AWS network. We build densely connected, multi-path data center networks, like the one illustrated here. These types of networks have a lot more capacity and a lot less oversubscription. We're able to do this cost effectively because we've invested in building super low-cost, high-capacity network switches and optics. All this networking capacity makes a lot of things better for us and our customers. Obviously, it means there's a lot of network capacity, so it's easy for applications to talk to one another. And it also means that when there's switch failures, there's always excess capacity available to route around those failures. So lots of great things to like here. But it turns out that traditional networking protocols are not designed to take full advantage of this sort of network. To understand why, let's look at the most popular networking protocol ever, good old TCP. TCP is a connection-based networking protocol that was designed to make programming easy and to help applications work in a wide variety of networking conditions, everything from the internet to traditional data center networks. And it works quite well in the cloud as well. One of the most important ways that TCP makes life easier for programmers is by assuring packets arrive in order without missing packets. And to accomplish this, TCP goes to great lengths to send all the packets for a TCP connection down the same path in the network. This largely assures that the packets get to the other side in order, which reduces the work for the TCP protocol. But because each TCP connection only uses a single path, it means that you can't take advantage of a network, a multi-path network like we have here. And it also means that if there's an issue in the network, say a slow router, even though there might be plenty of additional capacity in the network, you can't route around that network. SRD uses a different approach. It uses what's called network multipathing, deliberately sending packets across multiple different paths in the network. Now, this increases the throughput and allows SRD to detect and avoid any issues in the network. Now, naturally, this can result in packets arriving on the other end out of order, but SRD takes care of reordering and asking for packets to be retransmitted, all transparently. So multipathing, that's the first benefit of SRD on the AWS network. But there's other benefits. A second benefit is that SRD is able to detect dropped or delayed packets an order of magnitude faster than TCP. And that's because TCP's got to work in a number of different networking environments. Everything from the wide open internet to those legacy data center networks that we looked at earlier to the cloud. But SRD is purpose-built and optimized for the AWS network. And this means that retransmits will happen in microseconds rather than milliseconds. Finally, SRD benefits from the dedicated resources on the Nitro controller, whereas TCP uses the guest operating system. And this means that SRD is able to react immediately with no impact on your application. All of this means SRD provides significantly lower latency and higher network throughput than traditional networking protocols. Exactly what EFA needed to cater to the most demanding high-performance computing applications. Now, one of the cool things with performance innovation is that sometimes you invent something for one problem that ends up being useful for a lot of other things. And I think the canonical example in engineering is probably the wheel. And SRD is turning out to be the wheel of the AWS network. We built SRD to serve a very specific purpose, enable the most demanding network applications to thrive on AWS. But what we created, the ability to better utilize our massive data center network, holds the promise to help us reinvent and help customers in so many ways. So how do we give more customers the benefit of SRD? Well, EBS is an obvious place to start looking. EBS provides block-level storage to EC2 instances, and it's used by all sorts of mission-critical applications like I/O-intensive databases. And with block storage, performance matters a lot. And performance is not just about average performance. Outliers or tail latency matters a lot. If you need a specific block of data, it really doesn't matter to you if all the other data blocks are available. You need to wait until your block of data is ready. And this is the reason that tail latency can have such an outsized impact on applications. Having to plan for tail latency is something that I'm very familiar with. My morning commute involves driving or biking over a drawbridge. And on most days, the vast majority of days, the bridge is down, my commute is consistently fast. But every once in a while, the bridge is up, and it can take much, much longer for me to get to work. And given it's seemingly random when they decide to raise the bridge, I'm faced with a difficult decision. I either have to leave extra early every day in order to get to all of my meetings on time, or I run the risk that I'm late once in a while. Now, I'm not going to tell you what my strategy is, but I wish that I didn't have to make this decision. The trade-off of designing for worst-case latency or getting burned when you don't plan for it is a bummer in the real world, and it's a bummer with performance engineering. Let's look at tail latency in EBS. One of the places that EBS is most sensitive to network latency is writes. And that's because a successful write involves writing that data to multiple places for durability. Each of those replications is an opportunity for a dropped packet or a delayed packet. And write latency is really important because databases aren't going to proceed until they know that write has been acknowledged. So here we see the write latency of the current EBS IO2 volumes. And the 99th.9 percentile, the first data point, shows 999 out of 1,000 writes finish in less than 5 milliseconds. That's pretty good, unless you're unlucky. And then 1 in 100,000 requests take nearly 35 milliseconds. That's 7 times longer. And since we're in Vegas, it's worth remembering everybody gets unlucky sometimes. So here we see how things improve when we use SRD with EBS. Things are better everywhere, but they're especially better in the tail. In fact, SRD results in up to 90% reduction in tail latency. With performance like this, you don't need luck. And using EBS with SRD does more than just reduce tail latency. It increases throughput by 4x. So it's pretty clear that using SRD with EBS can have a huge performance impact for customers. So I'm excited to announce that starting early next year, all new EBS IO2 volumes will be running with SRD. And getting this improved performance couldn't be easier. You'll simply create a new IO2 volume and start getting lower, more consistent latency and higher throughput at no additional cost. Now, we are really excited about these results with EBS. But we asked ourselves, what more could we do with our SRD wheel? Could we provide more customers with the benefit of SRD without needing to adopt EFA? To do that, we need to look at ENA, the Elastic Network Adapter, which handles our general purpose networking. This is the standard network driver that you use with your EC2 instance. Good old TCP uses ENA. As discussed, ENA makes use of the Nitro controller to offload the work from the main EC2 server, allowing customers to use more of their resources for their workloads. So we looked at the work we were doing with SRD on Nitro and asked if we could bring that to ENA. Which is why tonight I'm excited to announce the launch of ENA Express. ENA Express brings SRD technology and its benefits mainstream by allowing you to bring it to any network interface. It's totally transparent to your application, and it works with normal operating system network protocols like TCP and UDP. You don't need to install any additional software or change your instance. You simply enable ENA Express on your ENA interface, and you'll start getting the benefits of lower latency and higher throughput. So how will ENA Express help your applications? Well, the first benefit of ENA Express will be reduced tail latency for low latency network applications. And this is just like what we looked at with EBS. But with ENA Express, you can get these benefits on any network-based service. A good example of this is Elasticache, which delivers very low latency caching over the network. As you can see, Elasticache delivers pretty consistent latency, even in the tail. Not bad, but can we do better? Again, we see SRD reduces latency all throughout the tail, but it especially reduces latency at the high nines. Elasticache support for ENA Express will be coming very soon, and to start using it, you'll simply enable ENA Express on your Elasticache client instance ENA, and then you'll magically get the benefits of lower latency and higher throughput. Speaking of throughput, because ENA Express takes advantage of SRD's multipathing, which distributes packets for each TCP connection over multiple paths in the network, it means that ENA Express will increase single flow TCP connections from 5 gigabits per second to 25 gigabits per second, 5x better. Now, this improved throughput is going to help your applications in a number of ways without requiring any changes to your code. Okay, so whether it's EFA for high performance computing, or EBS for storage, or ENA for your network workloads, SRD and Nitro are going to help provide better performance for your workloads. Okay, I mentioned earlier that performance is often a dance between hardware and software. Well, if we extend this analogy, there's no bigger dance happening right now than in machine learning. Hardware, software, network, science, it's a veritable hoedown of performance engineering. And that's because machine learning, performance is more important than ever. You can think about an ML model as a math formula with lots and lots of variables. The math used to create a new machine learning model is usually done on large multidimensional matrices, also called tensors, containing a huge number of floating point numbers. It's a familiar approach that's been used for decades to build models for everything from forecasting to personalization. But large foundational models have emerged over the last few years that can do some really incredible things. These large models can understand natural language, and they can even generate novel images, text, and 3D models. Really cool stuff. Here you can see one model's take on how to make a performance improvement to my Land Rover. The image is pretty cool, but LLMs aren't quite good at performance engineering yet. So it's still early days for what's possible with these models. But what we do know is that the capabilities of these models seems closely related to the number of variables within the models. Not only are the models getting bigger, but the step function changes in size and complexity are happening more frequently. While we see large models today being trained with 1 trillion models, it won't be long, 1 trillion variables, it won't be long until we see the next order of magnitude in complexity and scale, and hopefully even new capabilities. But just as exciting as the models and the capabilities is the performance innovation that's meeting the needs of these large foundational models. But what does that really mean? Model training involves iterating through training data and producing a large statistical model that best matches the data. The model is made up of variables that are referred to as parameters. In each iteration, a training algorithm adjusts all the parameters in order to reduce error in the model's predictive accuracy. Now, we measure the error as a function called loss. And when training a model, the goal is to reduce loss as much as possible. The lower, the better. And model training typically continues until further training no longer meaningfully reduces loss, a point that's referred to as convergence. Essentially, we train until we find an asymptote. When it comes to training performance, our goal is to reach convergence as quickly and cost-effectively as possible. So why is this challenging? Usually when you think about performance engineering problem, you try to identify one dimension that's holding you back, and you go to work on optimizing it. But the interesting thing about ML training workloads is there are so many potential bottlenecks. Each iteration of the model is computationally intensive. There's a lot of number crunching. So we need specialized hardware to do that number crunching efficiently. But as we discussed, models are getting really, really big, which means we need servers with large amounts of memory. And whether it's because we need more memory or more compute, we often find ourselves needing to scale across multiple servers. But ML models are huge graphs of interconnected parameters. And so when we divide our model across multiple servers, we end up needing to communicate frequently. And this communication itself over the network can become a bottleneck. So let's look at how we're innovating to remove all of these bottlenecks with AWS's purpose-built machine learning hardware. The TRN1 instance has 16 ML-optimized Trainium processors and 512 gigabytes of memory, providing our most cost-effective, high-performance machine learning instance. And to scale out, we need great networking. So the TRN1 provides 800 gigabits per second of high-performance networking connectivity using EFA and SRD that we described earlier. Now let's look at how we can use the TRN1 to train very large models. But first, one of the interesting decisions we need to think about is what data type to use to store our model parameters. Parameters are floating point numbers, but they can be computed on and stored at different precisions. And in computers, this is determined by the size of the floating point number. Using large floating point numbers gives you more precision. With machine learning models, higher precision generally improves the accuracy of the model, which helps you converge with fewer iterations of your model. But there's trade-offs to using larger floating point numbers. First, computing on 32-bit numbers is more expensive than computing on 16-bit numbers. So each iteration of the model generally takes more time. And of course, more bits means more memory and more data to send over the network. So there's trade-offs. But because most models perform optimally with 32 bits, that's where most ML scientists start. So let's start there as well. Here's our baseline run of a GPT-3 model with a 32-bit model. You can see we get good convergence with low loss and reasonable throughput. Actually, for 32-bit models, this is really great performance. When training GPT-3 at 32-bit precision, we can train 2.4 times faster and at 3.7 times lower cost than we can with the P4D, our current most optimized GPU instance. But how can we do even faster? Well, we can try using lower precision floating point numbers. And this will reduce the memory requirements and improve the computing performance. But many models train poorly with 16 bits. They either don't converge or they converge at too high a loss, like pictured here. This is not what we want. So ML scientists have worked to find a way to use lower precision parameters without the problem we just saw. And they ended up with something called mixed precision, where some of the parameters are stored at 16 bits and some of the parameters are stored at 32 bits. With mixed precision, most of the compute gets done at 16 bits. So that means we can train faster than we can with a 32-bit model. But because we still have to store and use 32-bit copies of the parameters, we don't get all the memory or speed benefits of that 16-bit model. All up, it's a pretty good place to be, and this is where most models are trained. But we asked ourselves if we could do even better. And last year, I discussed stochastic rounding as a possible way to get better performance and lower cost. And tonight, I'm excited to share some results. Now, just as a refresher, stochastic rounding is probabilistic rounding. So 0.3 no longer rounds to 0 deterministically. Instead, 70% of the time, it rounds to 0, but 30% of the time, it rounds to 1. Whereas 0.7 rounds down to 0 30% of the time, and up to 1 70% of the time. Machine learning scientists are finding that stochastic rounding can enable practitioners to use lower precision floating point numbers and get the benefits of larger floating point numbers. The problem is, stochastic rounding is a lot of work in most processors. Every time you round, you need to generate a random number and then use that number to round your floating point number. And as I discussed last year, one of the special things we did with Trainium is we provided native support for stochastic rounding. Let's look at how this helps our model training performance. So now, instead of mixing precisions, we store all our parameter state as 16 bits. And this means we get the full benefits of computing, storing, and sharing 16-bit numbers. And you can see that with stochastic rounding, we converge in the same place as we do with mixed precision or 32-bit precision, but we get there faster. In our testing, we're seeing about a 20% improvement using stochastic rounding compared to mixed precision. And while the results will vary from model to model, we expect that stochastic rounding will have a meaningful impact on performance for a number of ML training workloads. We're really excited about stochastic rounding, but it's only one of the ways that we're investing to improve the performance of machine learning capabilities. Let's look at what happens when we scale our training across multiple chips and multiple servers. The name of the game here is efficiency. The more time we can spend training our model and the less time we can spend communicating and sharing results, the more efficient we'll be. And higher efficiency means shorter training times and lower costs. Now, one of the most impactful ways to improve performance is to reduce algorithmic complexity. For those of you that took computer science courses, you'll probably recall this as big O complexity. Some algorithms scale very inefficiently relative to the number of things you're computing on. For example, an O of n squared algorithm scales with the square of the number of items you're computing on. So if you have 10 items, it takes order 100 time to compute. And if you have 100 items, it takes order 10,000 times to compute. So 10x more items takes 100x more time. Needless to say, these sorts of algorithms aren't very useful. You really want something that scales linearly, O of n, so that adding more items adds constant amounts of additional work. So 10x more items, 10x more work. And if you're really lucky, you want something that scales sublinearly, like O of log n. Okay, let's take a look at the algorithmic complexity of scaling with ML clusters. As we discussed, when you're training a model, you're doing a huge amount of computation against billions of parameters. And if you can fit your model on a single processor, you just have a single processor performing all that math, and everything works fine. But what happens when you scale this out because you can't fit everything on a single processor? Well, now you have multiple processors doing slightly different optimization in parallel. And that's good. That's what we want. The more of these that we can do in parallel, the faster we can train our model. Now you might think, okay, 4 processors, 1/4 of the time. Well, sadly not. Because after each iteration of the model, the processors all need to exchange information in order to reduce error in the next iteration. And this exchange of information is expensive. And in most cases, while it's going on, your model's not training, it's waiting. And this leads to longer and more expensive training runs. Let's look at this. The most naive approach would be for every processor to share its information with every other processor after each iteration. Here we have 4 processors, each exchanging parameters with each other on every iteration. This kind of looks like a lot of work, and it is. As we add more processors, the number of exchanges you do increases with the square of the number of processors, and that gets big fast. The exchange is quickly overwhelming to the processors. Even with extremely fast, low latency interconnects, in a large cluster, the exchange could easily take more than the time you're spent training. Now, fortunately, some savvy scientists observed that with machine learning, you can compute parameter averages incrementally. That is, each processor can take results from another processor, combine it with their own results, and hand it off to another processor. And by the time everybody combines their results with everyone else, you've received the same results as you would if one processor combined all the results on its own. Now, this opens up the possibility to vastly optimize the communication phase, from something that scales with the square of the number of participants to something that scales linearly. To understand how this works, imagine we arrange the processors in a ring. Each processor divides their memory into n chunks, where n is the number of processors. In our example here, we're going to divide it into 4 chunks because we have 4 processors. On the first step, processor 1 sends chunk 1 to processor 2, processor 2 sends chunk 2 to processor 3, and so on. So everyone sends one of their chunks to the next processor. And then everyone takes the chunk they receive and they average it with their corresponding chunk. On the second step, everyone sends the chunk they just received and averaged onto the next processor. And again, everybody takes the chunk that they receive and they average it with their corresponding chunk. We repeat this n-1 times in our example 3. And by the time this is done, each processor will have one fully averaged chunk. Now all they need to do is share that chunk with everybody else. And so there's an additional round where the fully averaged chunk gets shared around to all processors. Now this takes another n-1 steps, but all in, it takes us 2n-2 steps. So it's a little less than 2 times around the ring, and we've computed the full set of averages and shared it with every chip on the cluster. So let's see what the performance of this looks like. Here we see our new sharing algorithm and how it scales as we add more chips to our cluster. Now you actually see that for a long time, the time spent on the sharing step is constant. Adding a new processor doesn't make the averaging take longer. And this is a little hard to get your head around, but it boils down to the fact that the algorithm I just described is throughput bound for small cluster sizes. Basically, we have to move the data around the ring twice. And whether we have 4 processors or 40 processors, the time it takes to do that is based strictly on the size of the data I'm sharing and the throughput of the interconnects. But at a certain point, in our example, about 128 processors, every new processor makes the process take longer. And this is because the process becomes latency dominated rather than throughput dominated. And this is the linear scaling that we expected. And it's a huge improvement over what we described initially. But as machine learning models have gotten even bigger, even this algorithm can become a dominant part of your computation time. So we asked ourselves if we could do better. And fortunately, we had some inspiration. At Amazon, you may know that we have a thing about rings. And we're all too aware of the risk of having one ring to rule them all. So naturally, we asked ourselves if we could forge more rings. And it turns out that the same approach that allows you to compute averages incrementally will allow you to compute averages hierarchically, a ring of rings. And a ring of rings approach will turn our linear algorithm into something that looks much more like a logarithmic algorithm. So our new approach has two distinct phases. And in the first phase, each Trainium processor on every server averages the results with the other chips on the same processor. This is the same process we looked at earlier, and because our averaging algorithm scales on constant time based on the throughput on these Trainium servers is very high, so this part of the process goes very, very quickly. Then in the second phase, we run a second ring averaging process with one processor from each server. This looks also exactly like the original process I described, but now we're using one processor per server. And once the second averaging completes, each server has one processor that has the final averaged results. So at this point, all that needs to be done is those results need to be shared with all the other chips on the server. And now each chip has the fully averaged results, but in much less time. So you can see, just like our original linear ring algorithm, our new ring of rings algorithm has constant time scaling until the cluster gets to a certain size. And then, again, it starts taking longer with each additional server. But the scaling is much more gradual. And this means that we can scale to even larger clusters. In fact, when training clusters with a ring of rings, you can see a 75% decrease in the time it takes to average parameters. And while today we only use 2 levels of hierarchy in our ring of rings approach, if necessary, we could add additional layers to this hierarchy and improve scaling further. Now, I want to give a shout out to our collaborators at PyTorch Foundation for their help on this one. It's really meaningful innovation, and it should help train very large machine learning models. And of course, now that we have a way to scale even larger machine learning models, wouldn't it be great if we had a Trainium instance with an even faster network? So tonight, I'm excited to announce a network-optimized Trainium-based instance, the TRN1N. The TRN1N will offer 1.6 terabits a second of low-latency, EFA-optimized network bandwidth. This will accelerate innovation by allowing builders to train ultra-large models with even greater efficiency. Okay, this evening, we've been talking all about performance engineering and the lengths that we go to achieve peak performance. And when you think about extreme performance, there's one other industry I think that lives and breathes this every day, on and off the track, especially on Sundays. And to tell us more about driving performance innovation, please welcome Jock, Senior Race Engineer and Driving Coach for Charles Leclerc at Scuderia Ferrari.
AWS do things big, huh? Hi, everyone. It's a pleasure to be here in front of you tonight to give you some perspective on the competitive environment of Formula One racing. I'm a graduate of mechanical engineering, and I've spent more than 30 years in F1. A veteran of 500 Grand Prix, working directly with the drivers trackside. I've had the privilege of working with 8 world champions in the most technically challenging sport. And that challenge is laid down for all of the F1 teams, and it seems pretty simple. Huh? All we've got to do, within the realms of the regulations and the rules, is to produce the fastest car over 1 lap, the common goal, pole position. But it's not that simple. Because in a season of 20 races, does the fastest car at the first race of the season prove to be the fastest car at the last race of the season? Invariably not. It's all a trade-off. But what are those trade-offs, and how do we make sure that we're trading smart? There are three fundamentals, performance significant parameters in an F1 car. Aerodynamics, power, and weight. Over 10,000 components go to make up a modern F1 car. And of those, maybe 200, 300 have a direct impact on some or all of those fundamentals. Every part of that car has to pull its weight, and in the case of engine parts, quite literally. Throughout the design and build process, from blank sheet of paper to race ready, that's a process that takes a team of 600 engineers around about 6 months. We have to navigate a path that has never been trodden before. A path which leads to a destination that we have only imagined in our creative and innovative mind. And innovation is the key. We cannot stand still. We can't rely on the tried and trusted because the competition is simply too tough. This season, for example, alongside AWS, we've developed a ground speed sensor, a virtual ground speed sensor, off-car, based on AI and machine learning technology and using AWS SageMaker. This delivers more reliable and faster data to our engineers. And crucially, it allows us to save weight in a sport where every gram counts. This is innovation. And of course, we have to move on from design to the harsh reality of the track. There are many variables to think about the track. Weather conditions, tyre characteristics, variations from track to track. But this is racing. This is what racing is all about. That's the difference from design to racing. But racing is not an exact science. In striving to understand every aspect of performance, we gather data, lots of data, huge amounts of data, probably too much data. But F1 racing is a blend of hardware, software, this data we're talking about, and of course, human skill, the driver. The driver is the one part of this complex jigsaw that we haven't designed, we haven't built, and we certainly haven't programmed. Unfortunately, there's no Control-Alt-Delete on these guys. But the driver, from our point of view, is the intelligence that allows us to make sense of too much data. In a relative sport, there are no absolute solutions, and there's only a small margin of success. And we can think of it maybe as a Venn diagram. What is possible within the realms of science? Let's make the most responsive, reactive, performant car we possibly can. No, hold on. There's rules and regulations laid out by the governing body, the FIA. And then, of course, there's the human, the driver. Every driver is different. They all have unique skills. They respond to different cues. What works for Charles might not work for Carlos or Lewis or Max. Somewhere in that Venn diagram, we need to find the peak of performance, the pinnacle, where the thousands of performance differentiators come together. But these peaks are many, and we have to find the highest peak. We want to be climbing Everest when our competition scales K2. This is where the true value of the driver comes in. His ability to both identify and communicate. And communicate is the important thing there. Communication is everything. To communicate his interaction with the car, to guide our team of engineers in the right direction. There are a number of ways to reach that peak, but alongside those number of ways to reach the peak, there are hundreds of ways of getting it very, very wrong. And time is never on our side. On track, we face constant decisions. Every day, every hour, every minute, actually every second, we make decisions. Decisions which impact other decisions, deciding between options which are mutually exclusive. Do we want to trade off speed for cornering? Or do we want to trade off weight for reliability? Those trade-offs also vary from circuit to circuit. So if we contrast Austin, for example, with Monaco, very, very different circuits. The corners are much tighter in Monaco. 30 miles an hour as the slowest corner in Monaco. 100 miles an hour slowest corner in Austin. The weather in Austin is invariably a lot hotter than Monaco. Monaco's down by the sea, much more humid. And then there's the grip. Monaco is a street circuit. 1 million buses and cars have been over that tarmac by the time we arrive, leaving a film of oil and dust. The grip is really low. Austin, bespoke circuit, the grip is really high. And then we come to race strategy. I'm sure you all know about race strategy. How many pit stops we do, what tyres we choose to use. We are developing models for race strategy based on machine learning and game theory. There is no right or wrong strategy in a race because it depends on who you're racing against. It's a cat and mouse game with the competition. The decisions they make impact you. The decisions you make impact them. For example, leading a race is very, very different from being in second place. In second place, you can quite literally see what your opponent is doing. If you're leading a race, you don't have that visibility. There are only trade-offs. And we have to make sure we're trading smart. All of these decision points are opportunities for us to make the right decision or the wrong decision. To make those circuit-specific decisions, those strategy calls, we need to use our skill and judgment as engineers, analyzing data to strive for the fastest lap, the best strategy, the fastest race. And at Scuderia Ferrari, we're wanting to bring that experience closer to the fans. To do that, next year we'll be launching the Scuderia Ferrari app, powered by AWS and using AWS Analytics to deliver the best experience for our global fan base. This mobile app will provide exclusive interviews with drivers, engineers like myself, as well as exclusive content allowing our tifosi all over the world to get a backstage pass to the Scuderia. Stay tuned. Thank you for having me today, and I hope to see you again at the track. Thank you.
Thank you, Jock. I have to say, when I was first asking Jock to come to my keynote, I wanted to drive a Ferrari out on the stage to kind of kick off the performance theme. And he said to me, "You know every gram matters." And I think what he meant by that is I probably wouldn't fit in a Formula One car, but anyway. I'm looking forward to what Ferrari comes up with for the 2023 season and the new app. Okay. I spent the first part of our talk taking you deep into our investments in Nitro and Trainium. And not just the chips, but the software innovation to help us get great performance for a wide variety of workloads. But our deep investment in performance is happening across all of our services at every level of the stack. So to wrap up this evening, I'd like to dive deep into how we're improving performance in a very different area, serverless computing. AWS launched the first cloud-scale serverless computing service, AWS Lambda, in 2014. Behind me, you can see a youthful Werner Vogels describing his enthusiasm on this very stage. Lambda gives customers an easier way to build highly secure, highly available, high-performance, cost-effective applications without the need to manage any infrastructure at all. No instances, no containers, no undifferentiated patching. With serverless computing, you just focus on the code that provides your customers with differentiated capabilities. We've come a long way in the last 8 years. We've added more than 100 new features since launch, including support for Graviton, longer function durations, and millisecond billing. And today, Lambda's in use by over 1 million customers, like Capital One, Liberty Mutual, and Coca-Cola. And they're making over 10 trillion monthly requests. Serverless computing is changing how applications are being built. And of course, a big part of that is performance. I mentioned at the start of tonight that we always seek differentiated performance, but never at the expense of security or cost. So let's start this story with a fundamental design decision that we made when we built Lambda. At its essence, Lambda executes your function code in a fully managed runtime environment. In the case of Java, that would be a fully managed JVM. Now, in our very technical drawing behind me, you can see a managed JVM, the table, running our friend a single user function. But to make Lambda work efficiently and scale seamlessly, we need to make it a multi-tenant service. Multi-tenancy allows us to use a large share pool of capacity to give customers the elasticity and low cost that they expect from the cloud. Multi-tenancy is core to everything we do at AWS. But doing it right requires careful engineering. Let's have a look. The simplest way to achieve multi-tenancy for a service like Lambda would be to run all of the customer functions in the same runtime environment. But the languages and runtimes supported by Lambda have no concept of multi-tenancy. Functions would be able to read and write each other's memory. This wouldn't work. Another obvious solution to this problem would be to use multiple runtimes running as separate processes. And at first blush, this would seem like a reasonable solution. An approach like this is tempting because processes are quite efficient at sharing resources. And before we launched, we actually had many long debates about whether this sort of process isolation was adequate. But ultimately, we decided that process isolation does not provide the isolation and security that we and our customers require. Instead, we decided that AWS requires virtual machine level isolation for every runtime environment. Now, why is a VM a better way of isolating a workload? To illustrate this, let's look at a historical example, the castle. The castle is an age-old approach to secure isolation. And while there's certainly been a fair bit of design innovation over the millennia, castles largely share a common design principle: limit the number of access points. Large, strong walls and design elements like moat are used to protect the castle from intruders. And egress and ingress is typically limited to a small number of well-defended entry points. This is also how virtual machines are built. A virtual machine only has a few narrow access points, and it's designed to share nothing with other virtual machines. Now, I tried to find a good example of a castle with lots of access points, but I came up empty-handed. Either no one was short-sighted enough to build such a castle, or the ones that were built simply didn't persist. Every door is an access point, an opportunity for an attacker to breach your defenses. And that's the problem with operating systems. Operating systems are secure and trusted for many purposes, and they mostly do a good job of securing things. But mostly secure isn't good enough. Operating systems have hundreds of different system calls to let processes interoperate efficiently. And those system calls provide considerably more surface area for attackers to try to breach. It's not a theoretical issue. Every year, there are dozens of new privileged escalation and side channel attacks discovered in every major operating system. And this is why we made the decision that AWS services, we always use a virtual machine to isolate customer compute workloads. Surprisingly, other cloud providers have come to a different conclusion, but not us. In fact, we're not even satisfied with the isolation provided by traditional hypervisors. And that's a big reason we built the Nitro hypervisor, which further improves security and isolation by using the Nitro chips we discussed earlier. But that's a story for another night. Tonight, we want to talk about how we optimize Lambda performance over the years. So, with this context, you can think of Lambda as a big cache, where the items being cached aren't datum, but they're units of compute. And the cache isn't a pool of memory, but it's a big pool of computing capacity. And to make things efficient and secure, we divide the capacity up into a large number of virtual machines, or slots. In a data cache, slots are just entries in the cache, usually held in memory for speed. But in our compute cache, each slot is a virtual machine that is standing by, ready to run a customer's function. When we built Lambda 8 years ago, the EC2 T2 instance was our state-of-the-art approach to virtualizing small workloads. So we built our compute cache using T2 instances. Each slot in the cache was a T2 instance with a runtime environment that was loaded with the code for a particular customer's function. Each slot could be used to run that same customer function as many times as needed. But each T2 instance was only used for one customer's function. The slot could not be used for different functions. And if we wanted to do that, we had to shut the instance down, relaunch it, and reinitialize it with a new function. So with this context, let's look at how Lambda handles requests. When a customer invokes a Lambda function, the request is routed to the Lambda front end. It then goes through a routing layer that matches the request to an available slot that can handle that particular function. This is the happy case, a cache hit. But what if we don't have the requested function in our cache? That's a cache miss. And with Lambda, a cache miss means that we need to create a new slot to run our new function. Now, T2 instances launch pretty fast, but nowhere near fast enough for a function call. So we need to reserve part of our capacity pool as uninitialized T2 instances. And this allows us to avoid the launch latency. But it means that we have less capacity in our cache to hold functions, which in turn means we have more cache misses. And even with this capacity standing by, it takes significantly longer to instantiate a new function than it does to execute a function that's already in the cache. And we call this process a cold start. And these cold starts are a form of tail latency. And what a tail it is. Here's the performance when we first launched Lambda. In this case, we're showing a slightly different performance graph. This is showing you the frequency of requests at each latency. And this view is going to be interesting because we can really see the cache in action. Here you see the cache hits, that big mountain. This is the really fast side of the graph. This is where we want our requests. But let's look closer at the tail. Here, we see a second set of requests creating a smaller bump. And these are our cold starts. This bump is way smaller, so we needed to zoom way in, but it's also way slower. Cold starts don't happen often, but when they do, things are a lot slower. Now let's be clear. Cold starts are not a system failure. Caches are great at reducing average latency, but they only work when you have what you need in the cache. So what causes Lambda to not have a function cached? Well, the obvious thing is when you haven't used the function in a while. And that's not ideal, but customers generally understand it. The more interesting reason is load related. Here's an example workload. In the world of microservices, load changes like this are not that uncommon. While Lambda's compute capacity may be adequate to handle demand most of the time, as request spikes like this happen, new provisioned capacity will have to be provisioned. And unfortunately, this means that just as things get busy, Lambda slows down. And that's not what we want. So how do we reduce the number of cold starts and make Lambda deliver more predictable capacity? The obvious solution is to use a bigger cache. A bigger cache allows us to hold more items in the cache and therefore increases the probability that we have what we need when we need it. But there's a problem. A larger cache means more cost. And as I discussed, The real goal is to provide remarkable performance at the lowest possible cost. So how do we put more in our cache without adding cost? To do that, we're going to need to make the cache more efficient. And this is where Firecracker enters the picture. Firecracker is our purpose-built virtualization technology, which provides secure and fast virtualization for serverless computing. The virtual machines are significantly smaller than regular virtual machines, so small that we call them micro VMs. And Firecracker enables us to launch micro VMs in a fraction of a second. So Firecracker combines the security and workload isolation of a traditional VM with the efficiency that generally only comes from process isolation. Here's our trusty compute cache from before. Let's see how Firecracker helps us. Firecracker allows us to pack more slots on the same hardware because micro VMs are much smaller. And this means we get a bigger cache without increasing cost. And a bigger cache means more cache hits and fewer cache misses, or cold starts. But Firecracker helps us in another less obvious way. Firecracker is optimized to allow us to shut down and restart virtual machines in fractions of a second, rather than the seconds it takes with a T2 instance. And this means we no longer have to proactively remove things from our cache. And this enables us to leave existing functions running longer. And this too equates to an even larger effective cache on the same capacity. So let's look at the performance after we launched Firecracker. Here's the same performance graph we looked at earlier, still zoomed in on our cold start hump. Let's see the impact of the more efficient cache. With Firecracker, as expected, we were able to reduce the cold start latency rates on Lambda by 50%. And that means a smaller bump. But that's not all. Since we launched Firecracker, we're actually attracting more spiky, less predictable workloads. And the cool thing about this is we're able to maintain the 50% reduction in cold starts despite these spikier workloads. And this is the cool thing about performance engineering. When you make a big improvement, you open up your service to new workloads, which in turn inspires you to seek further performance optimizations. And that's exactly what happened. But the problem with caches is no matter how big they are, you eventually have a cache miss. And if the time it takes to handle the cache miss is significantly longer than the time it takes to handle a cache hit, you're gonna get a bump. So if we really want to improve tail latency with Lambda, we're gonna have to make those cold starts faster, much faster. So let's look at what happens when we get a cold start. When a cold start occurs, we first instantiate a new micro VM from a managed runtime environment needed by the function. So this is a common snapshot. And this has all the language and language runtime pre-installed. And with the optimizations we have with Firecracker, this happens very quickly. And then we need to transfer and load the customer's function code into the new runtime environment. And the time taken here can vary based on the language and the amount of code in your function. But with the fast EC2 network, this is a very small portion of the average cold start. Now, once the code is loaded, we need to do a process called initialization. This time also varies extensively based on the language and the actual code. For example, in Java, the language with the longest cold start times, it's driven by three main factors: the startup time of the JVM, the decompression and loading of the class code, and the execution of the initialization code in the classes. And it's typically the last of these steps that drives the long cold start times. And that's because Java essentially allows unbounded execution during initialization, a capability that apparently many Java developers find too hard to resist. But what's interesting is, at the end of the initialization process, you're basically at the same spot. So imagine that after the initialization is complete, we take a snapshot. And then when we need to boot a new micro VM to handle that function, we start with this snapshot rather than the common snapshot. And this would allow us to avoid initialization entirely. That would be cool. This could actually make cold starts so fast that they'd be indistinguishable from cache hits. Well, tonight, I'm excited to announce Lambda SnapStart. Lambda SnapStart significantly decreases the Lambda cold start time. SnapStart is built on Firecracker snapshotting functionality and a few innovations I'll describe in a second. And snapshots available tonight at no additional cost. Okay. Before I tell you how it works, like any good cooking show, let's look at the results. All right, here's our trusty performance graph one last time, and our all too familiar bump. Let's take a look at the impact of SnapStart. Boom. That's it. No more hump at all. That's pretty obvious, right? And that's because AWS Lambda SnapStart reduces cold starts by up to 90%, making cold starts virtually indistinguishable from cache hits. So let's quickly look at the innovations that allowed us to achieve these results. Our first innovation is assuring uniqueness. Now, I said a moment ago that the initialization process is largely the same. And that's true. But there are small and very important exceptions. Specifically, some operating systems and languages need to generate and store unique numbers. One such class of functionality is cryptography, which requires a high degree of randomness. And the way that randomness is achieved in modern software is by using pseudo-random number generators. And the way these pseudo-random number generators work is they generate a unique seed, and they use that seed to generate random numbers. Now, if this seed is generated during the initialization step, as it often is, then it will be stored in our snapshot, and it will be the same on all micro VMs that are ever instantiated from that snapshot. And if this seed is the same, then the random numbers won't be very random at all. And that would have serious implications for security and correctness of cryptographic algorithms. So, to avoid this, we need to find the critical sections of code that generate these unique numbers and update them so that these numbers are initialized after we restore the snapshot. You can think about this as creating a mini ultra-fast initialization step, but it only does the things that have to be done after the snapshot is restored. It's not a lot of code changes, but it's really important. This is not all that different than writing thread-safe code. But in this case, we're making the code safe for snapshotting. We've updated Lambda's managed runtime environment, execution environment, and common libraries to be safe for snapshotting. And we're currently upstreaming these changes so the broader community can benefit from this. And it's highly likely that all you need to do to use SnapStart is use these updated packages. But if you happen to be doing something uncommon, like implementing your own custom cryptographic library, we also provide detailed guidance on how to modify your code to make it safe for snapshotting. Okay, our second innovation addresses efficient snapshot management. Now, taking and managing unique virtual machine snapshots for every Lambda function that could possibly ever be executed sounds easy, right? But of course, at scale, it's not. We have tens of millions of Lambda functions registered. And if we needed to store a unique snapshot of all of these that included the OS and the language runtimes, we're going to have a pretty expensive storage bill. And it could also prevent us from efficiently moving that data around, which could actually work against our performance goals. Now, we made the observation that if you compare the snapshots of 2 or more Lambda functions for the same runtime, the vast majority of the snapshots are the same. The OS is the same. The language runtime is the same. The only part that's different is the function code itself. And that's a relatively small part of the data in the snapshot. So by constructing our snapshots incrementally, we can build off a base snapshot and create smaller snapshots for functions. And these smaller snapshots will mean better performance and lower cost. Now, there's actually a fair bit of nuance here in how we do this. For example, we encrypt the base snapshot with our service keys, but the function snapshot is encrypted with customer supplied keys. But conceptually, this is how it works, and the results are really good. In fact, these incremental snapshots are only about 10 to 20% of a full snapshot. And this means we can store and distribute a large quantity of snapshots very efficiently. Okay, our final innovation helps assure that we can boot our micro VMs with minimal latency with an approach that we call predictive snapshot loading. And to understand how this works, think about streaming your favorite Middle-earth adventure story. You don't need to download the whole episode to start watching. You just download just enough to start watching, and then the rest fills in while you watch. And this is kind of how a virtual machine boots. You can start booting it once you have the first few chunks of the snapshot, and then load the rest while it's booting. The problem is that when a virtual machine boots, unlike a human watching a video, it jumps all over the place. And for those of us with less than amazing home internet, you know what happens when you jump around too much. You get stuck waiting. And fortunately, when a virtual machine boots, it doesn't jump around randomly. In fact, it's very predictable. Like when you sit down to watch all your favorite Rings of Power scenes. Now, there's probably a few of you in the audience that haven't watched yet, so I'm not going to ruin this. But I find myself returning to my favorite scenes often. 61 minutes into episode 6 is pretty amazing. 67 minutes into episode 8. You just watch it again and again. Virtual machines boot like this. They're very predictable. And so here we find our third innovation. With SnapStart, we profile how the virtual machine accesses every snapshot during its boot sequence. And then we use this information to predictively load the chunks the next time it boots. And this means that micro VMs are never blocked waiting for a snapshot to load. And this is what makes SnapStart so fast. We have customers like Capital One, Genesis, and Thundra, and Bill.com, all of whom have been using SnapStart and seeing massive gains in their early testing. And they've done it all with no code changes. So, if there's one thing I hope you take away from tonight, besides the beer, it's that performance work is never done. Which is why at AWS we're always innovating to provide you the best performance at the lowest cost without compromising on security. Across everything from custom silicon to Nitro, to the latest EC2 instances, to pushing the boundaries of serverless computing, we will continue to innovate to provide the best performance. Now, in our short time this evening, I've only been able to cover a fraction of the investments we're making across AWS. Fortunately, we have a number of sessions throughout the week that go much deeper, as well as discuss other performance-related innovations. I've picked out a few of my favorites and encourage you to check them out. As always, I've had a great time sharing a little peek underneath the hood of AWS. Thank you for coming to Monday Night Live, and enjoy the rest of reInvent.